Vasumani sir, welcome.
Hi. Thank you.
Hi, Ji. Very fine, Ji. Are you able to? Can you check that whether you can able to share your slides, Ji?
Yes. Can you see my screen?
Yes, Ji. Available. It's clear. No problem.
Okay.
Shall I formally start the session, Ji?
Yes.
Okay.
Shall I?
Yeah, wait a second. I'll just give an introduction, then.
Okay. Yeah, sure.
So, welcome all for the last day of the ATAL online FTP on the Revolutionizing electric powertrains, the role of wide-bandgap semiconductors in overcoming challenges and shaping future trends. Today we have Mr. Engineer Vasumani as from L&T Technology Services. I'd like to introduce Engineer Vasumani. Engineer Vasumani did his BE in Electrical and Electronics Engineering from Government College of Engineering, Tirunelveli in the year of 2018. Then he did his MTech as an integrated learning programs from BITS Bilani in the year of 2024. He has served as embedded programmer at VA Microsystem Private Limited from the year April 2011 to Jan 2014, and he has worked as an embedded developer for power electronics and motor control applications. Later, he joined as an R&D engineer in Tech Power Solutions from Jan 2014 to November 2017. Then he continued his service as a senior embedded engineer at Mark Controls and Systems Private Limited, and he worked as a senior embedded developer for power electronics application. Worked in inverters, frequency converters, SCR-based converter, and battery charger projects. In later, he joined as a senior engineer at Sona Comstar over in the year of 2021 to 22, and he worked as a senior engineer there and have worked on BLDC motor types of projects. He had experience in sign PWM and space vector modulation techniques of the BLDC motor control, and model-based system design is also done by him. He joined at L&T Technology Service from the year Jan 2022 as a lead engineer. Then he has promoted as a technical manager at November 2024 till present. Sir, his expertise in embedded programming, power electronics, motor control, MATLAB, textile instruments, microchip, STM32, NXP S32, Infineon, and Renesas. Now I request Mr. Vasumani to go ahead with the session.
Yeah.
Thank you, sir.
Yeah. Thank you for your nice introduction. It's a great opportunity to talk about this power electronics domain. And so today I'm going to talk about this switching behavior and efficiency in power electronics applications. Yeah. So the first content is what is switching behavior? And switching behavior includes a turn on and turn off process of. Can you hear me properly?
Sir, yes, sir. We are able to hear. Yes, can you please share your slide once, sir, please?
It is sharing. You can't see my screen?
No, sir. 1 second, please share. No, sir, please.
Yeah. Can you see my screen now?
Yes, sir. Yes, sir. Perfect, sir. Please go ahead, sir.
Yeah. So today I'm going to talk about this switching behavior and efficiency improvements in power electronics applications. And the first content is switching behavior. The switching behavior includes turn-on process and turn-off process of the switching devices like IGBT and MOSFETs. So we'll discuss about this turn-on and turn-off process deeply in the upcoming slides. So then what is the importance of power electronics applications? So nowadays, power electronics applications are booming And in futures in this world won't run without any power electronics and embedded systems. If you get into this automotive domain, EVs are running with the power electronics and embedded system. Like we need an inverter to run the motor, and to control the inverter, we need a microcontroller and embedded firmware. Other things other than this motor control, cluster is running in embedded system, and EC is running in embedded system, and we need a embedded system to turn on the air brake sensors and all. So if we go everywhere, it is running with a power electronics and embedded system nowadays. So and if we get into this power domain, actually transmission is there, actually AC transmission is there. So we need inverters to control those power, how to feed the control, how to observe the control, how much power we need to feed, how much power we need to observe. So those things are depends on this power electronics and embedded system. So in future definitely it will not run without any power electronics and embedded systems. So then what are the things we need to consider to improve the efficiency? So efficiency is nothing but the output power versus input power. We need to get more input power than output power what we require. So if we take example of our regular life, we are taking more extra things like proteins, energy drinks, other than that normal food to increase our energy. So like that, so input and output will not be same always. So the losses will be there inside our products. So we need to consider about losses to improve the efficiency. What are the losses we need to consider is switching losses, conduction losses, and then gate driver losses, etc. So we'll discuss these things deeply in the upcoming slides. So what are the switching devices are there? So MOSFETs and IGBTs nowadays GaN and SiC devices are booming, and so earlier they have used thyristors like ICR, TRIAC, and other switching devices. And when it moves to that MOSFETs and IGBTs, it was giving better efficiency than thyristor families. So nowadays, again, the GaN and SiC devices are giving very less losses than MOSFETs and IGBTs. So next, if we move on to this MOSFET switching characteristics, 10 on and 10 off behavior is there. So while we have a gate, drain and source terminals are there in MOSFET, and gate collector and emitter terminals are there in IGBT. So to turn on these MOSFET or IGBT, we need to give a gate pulses. So if we give the gate pulses, it won't turn on immediately. This is the gate pulse when it is giving high from 0 to high 3 volt. So at this time, MOSFET will turn on. So if we see this voltage across this MOSFET, so it will turn on. It will not turn on immediately. So it will take time. Some delay will be there because of this efficiency are reducing, because of losses are increasing. So while turning off process also, if you see like this, when it is giving low voltage from high voltage, it will take time to discharge to put to zero voltage, turn off. And because of this, also efficiency will reduce. So what is the reason for this delay? So internal resistance will be there in inside the MOSFET and IGBT, and internal capacitance will be there. So because of those things, it will make delay to turn on and turn off process. So because of this, it will reduce the efficiency also. And what is dead time and losses? So if we consider half bridge inverter, if we consider half bridge inverter and two MOSFETs will be there, we will connect a DC bus voltage here on the top and ground on the top. So if the both devices in on stage, the DC bus will get short circuit. So to avoid that, we are giving inverter pulses for the top MOSFET and bottom MOSFETs. So even it will create short circuit in between the rise time and fall time. So we have to consider some delay between in that turning on and turning off of the both the MOSFETs. So that means a dead time. So while the higher MOSFETs turns off, it will take time to delay to turn on the second bottom MOSFET. So that is the dead time. So if we are doing this, it will not cross the voltage and current will not cross. It will reduce that short circuits. So we need to give some dead time to turn on and turn off. So it will reduce the losses. So how much dead time we need to give based on the losses we have to calculate. So and then comparison of IGBTs and MOSFETs to improve the efficiency. So usually it is depends on the frequency, losses, voltage rating, and efficiency and application. So based on the applications, we are going to select that switching speed and voltage rating. So for example, if we take a battery charger or a solar battery charger, so the solar will give 17 to 20 voltage output. So we need to convert that into 12 voltage for the battery. Or either if we go for the boost converter, we need to consider 24 voltage more than that. So based on the voltage rating, based on the application, we have to select the voltage rating. And then switching speed. The switching speed is depends on your magnetic things, inductors, the size, and so the higher switching speed is depends on this again switching devices, which MOSFET, which switching device we are going to use in our application. So if you consider MOSFET, it will work till 1 megahertz, 2 megahertz like that. And if you consider IGBTs, it will not work beyond 20 kilohertz. So it will run in the slower speed. So and MOSFETs will run in the higher speed. So when we are going with a higher speed or higher frequency, the conduction losses will be reduced. The conduction losses based on the on time. So if we increase the frequency, the on time will be reduced. So the conduction loss we can reduce. And if you consider IGBT, the conduction losses will be more. The on time, when we reduce that switching frequency, when we operate less than the 20 kilohertz, the on time will be more. So the losses will be more in IGBT than MOSFETs. And then we have to consider switching losses, we have to consider conduction losses, and efficiency. So the efficiency will be high in MOSFET and than IGBTs. So then application scenarios where we are using which devices on GAN, IGBT or MOSFET or SIC things. So based on the applications, if you consider the SMPS switch mode power supply, and the SMPS usually used in computers, laptop chargers, and inside the CPU. And then so DC converters will be considered as SMPS also. So either the buck regulator or boost converter or buck boost converter, anything. So usually in the if you consider DC to DC converter, normal buck converter, boost converter, or buck boost converter, the switching losses will be more. So to reduce, if we are considering switching losses will be more. To reduce that, which is the best device? If you go with the IGBT or normal MOSFET, it will create more losses and it will reduce the efficiency. So we have to consider GAN or SIC devices. And then some PWM techniques are there, and LNC inductor and capacitor will be there in that. So if we consider this optimization approach as a switching, soft switching, is a PS zero voltage switching and zero current switching. So we can even reduce more losses. So it will improve the efficiency. And if you go into that motor control applications or inverter, solar inverter, so we need an inverter and switching, six switching devices will be there. And there we need a high power inverter. So usually the motor drives and the applications, it is running with a 33 kilowatt motor or a 45 kilowatt motor, 66 kilowatt motor. So when we are going for the higher power applications, the conduction losses will be more. The conduction losses it depends on the current flowing, how much current is flowing. And when we are going for the higher current, the power will be more and the conduction losses will be more. So that we are giving a suggestion to go with the IGBTs and the SIC MOSFETs. And so optimization approach, there will be an internal resistance, on-time resistance, off-time resistance, gate resistance will be there. So we have to consider those things also. So usually the losses will is equal to V is equal to IR. That is the loss voltage. So that when the current is increasing, if you go with the lower resistance, the voltage across the losses of voltage will be low. So it is proportional to the current and resistance. So the current is depends on our application, and resistance is depends on our device which we are going with. So if we go with a lower on-time resistance, it will reduce the losses again. So the same thing, EV inverters will work based on that, and HVDC and railway applications will work in the megawatt applications. So if you go for a higher power, again the conduction losses will be more. And for the megawatt applications, these SiC MOSFETs and normal MOSFETs are not available in the market. So the MOSFETs are available for 100 ampere, 200 ampere only, and IGBTs are available for 1000 ampere, 200, 2000 ampere like that. So when we are going for the high power applications, we need to consider IGBTs. And then RF and 5G systems. So it is depends on the switching losses. For RF and 5G systems, we need only low power converters, inverters like that. At that time, for the low power applications, current will be less, conduction losses will be less. So we need to consider switching losses. Why this RF and 5G applications will work on that very high frequency, ultra high frequency. So for the higher frequency, very high frequency, we need to reduce the consider the switching losses, and we need to go with a SiC or GaN MOSFETs. The GaN MOSFETs, GaN or switching SiC MOSFETs will come with a very less switching losses. This is based on application scenario, and switching losses. And so what are the switching losses are there? So there are two switching losses: conduction losses and then switching losses. Sorry. So conduction losses, when it is occur, when the device is on, the current is going to flow, and based on the current, conduction losses is going to occur. Right. So it is depends on MOSFET resistance again. So internal MOSFETs will be there. So maybe 0.5 ohm, 0.2 ohm will be there. When we are increasing the current, the voltage will be drop across those resistance, internal resistance. So we need to go with a lower resistance. Again, if you go to this switching losses, so switching losses will occur only on the switching transition when we are turning on the MOSFET from off state to on state, and off state to on state. That is on state to off state. So when the transition is happening, the switching losses will be occur. So to reduce that, we need to consider gate driver circuits and adjustments and internal gate resistance and all. So this is zero voltage switching and zero current switching. So it's nothing but a soft switching. So what we are doing, we are going to give the gate pulses to the MOSFETs. It will turn on and turn off. That is a hard switching. So what is soft switching? What soft switching is working based on snubber circuits. So we have to add some snubber circuits, RC snubber and RCD snubber. Some snubbers are there. Based on the snubber circuits, it's going to reduce the it's going to reduce the losses based on the time delay. So usually the zero voltage switching is so when it is going to zero, the current should not cross. So if you see here, the current is high, current is going down from the high to low, and the zero, the voltage is from it's going from zero to high. So usually. So if you take this MOSFET, when we are giving gate pulse to here, the switch will be on. So the voltage across the switching device will be zero. The current is going to flow. When we turn off the switching device, either MOSFET or IGBT, the switch will be off. So the current will be zero, and the voltage will be high voltage. So those voltage transition will happen from off to on or on to off. So this transitions, while this transition, the voltage will come low and the current will go high. So this should not cross. This should not. If this crosses, again there will be a power loss across here. When the voltage is high, when the current is flowing, crossing, so the power is equal to V into I. When the voltage is zero, if the current is flowing, the power will be zero. So the losses will be zero. And again, if we consider the on state, the off state, the voltage will be some voltage, 50 voltage, 100 voltage, whatever. It depends on our application. If we consider high 50 voltage or 100 voltage, the current should be zero. It should not cross. So the V into I is equal to zero again. So in this way, we can reduce the losses, power losses or switching losses. So that depends on our gate driver circuits that we will discuss again. Next thing is gate driver. This is going to give the gate pulses to the switching devices. So when we are connecting, so why do we need a gate driver first? So we are going to operate the switching converters, IGBTs or MOSFETs from the microcontroller using microcontroller. The microcontroller is going to generate a PWM pulses. So the microcontroller is working on the low voltage devices. Low voltage means five. It is operating on 5 voltage or 3.3 voltage something. But the power converters, the IGBT or MOSFET will work in the high voltage applications, like 100 voltage. We need to give a high 100 voltage, 200 voltage, 400 voltage, depends on our application. So if we connect that, we can connect the microcontroller to the MOSFETs directly. So the ground will be connected to the MOSFETs. Though microcontroller will also get the high voltage currents through the ground. So we have to isolate the microcontroller and high power devices. So to isolate that, we are using this optocoupler. So these gate drivers will come with the optocoupler inside. There will be isolation. It is operating based on that photo transistor. So when we connect the PWM pulses to the microcontroller, so it is going to generate PWM pulses, and it is given to the gate driver, and it's going to operate. So we will get the output PWM pulses based on that supply voltage, gate driver supply voltage, and ground will be isolated here. So for that, we need a gate driver for the isolation of microcontroller and power converters. Then we have to amplify that voltage of the gate pulses. So why the MOSFET or IGBT will work on that 10 voltage or 15 voltage. So if we take that look into that MOSFET characteristics or IGBT characteristics, it will turn on after the high pulses crossing 10 voltage or 15 voltage something. This depends on their manufacturer again. So some manufacturers giving 10 voltage, some manufacturers giving 15 voltage, 20 voltage like that. So we are going to generate a gate pulses from the microcontroller of 0 to 3 volt or 0 to 5 volt, but the MOSFET won't turn on. So we need to amplify that high voltage to 10 voltage or 15 voltage or 20 voltage, depends on that manufacturer device. So to amplify that, we are using gate driver. So when we are giving 3.3 voltage pulse here, so we need to give a different isolated power supply here to the gate driver. So so when it is on, the opto LED is going to give the turn on this opto transistor. Again, it will conduct this power supply. This is VCC is equal to the power supply, where you have to give an isolated power supply, and it's going to give the voltage what we are giving here. So we give 10 voltage, it will give the 10 voltage PWM pulses. And if we give 15 voltage of amplitude, it will generate a 15 voltage amplitude of PWM pulses with the same frequency what we are giving here. So then again, the gate driver is used to isolate the microcontroller and high power application and to amplify the PWM pulses. So then recommended gate drivers. So again, if we give the PWM pulses, there will be a delay between the input and output. That is called a propagation delay. So this gate driver also, if you give the pulses from the microcontroller, the LED won't turn on immediately. It will take some nanosecond or microsecond to generate the PWM pulses again in the output. So that is called a propagation delay. So based on these applications, again, we need to select the gate drivers. So if we go for this SMBS and DC to DC converter application, we need a high speed and low propagation delay gate drivers. And if we go for this inverter, EV inverters or industrial motor control drives, there we will use a high power inverter, high power motor. So we will go for a high power inverter. So the current will be more. So we have to go with the IGBT. So the IGBT IGBT drives with a negative gate voltage control. So the reason is, so when we give 10 voltage, 15 voltage, the IGBT will turn on, and so the turn off process is that if we give 0 voltage, the IGBT won't turn on. So we have to give an apply the negative voltage to turn on the IGBT. So we have to consider negative voltage gate driver control. And then for high frequency application or telecom application, so we have to go with the ultra fast gain gate drivers. The why? So these high frequency RF and telecom applications will work in the very high frequency things. So there is a limitation for this gate driver also. Yeah, some gate drivers will operate only 20 kilohertz, 50 kilohertz, 100 kilohertz, like that. So we need to consider the ultra fast gate drivers ICs. And then for high power applications again, so and the HVDC and grid inverters will work in megawatt. So definitely we'll go with a IGBT. So those things we need to take care of isolation also. It is coming with the isolations usually will say 3 kilowatt isolation, 4 kilowatt isolation. So these are all standards. So we need to think about these isolation voltage levels of the gate drivers for the safety. So, and then thermal management strategies are there. So when we are using our converters for the long time, for 1 hour, 10 hour, 15 hours, like that. So that is based on that application. So if we consider UPS, it is going to run only when the AC supply is not available at home. It may be for 1 hour or 2 hours. So, but if you consider a defense application, military applications, these converters they are using for missile applications. So the missile applications, it may work for 3 hours, 4 hours, continuously. It will work for 2 days and all. So when we are operating our converters continuously for 1 day, 2 days, it will generate a heat based on that switching and current. So based on that thermal heat, it will generate again losses again. So we have to consider those things also. How to manage the thermal heat? So we can use a heat sinks for the switching devices and the high current devices. So usually the all the load current will go through our switching devices like MOSFETs and IGBTs. So we need to make a heat sink for that to dissipate the heats. And then inductors and capacitors will generate a heat also, but we can't make heat sinks for that. So for that we have to add give active cooling techniques. That is based on the fan, cooling fan. So usually we will use a cooling fan and two cooling fans. One will suck the air from the outside, and again the another fan will push the hot air to the outside. So these kind of active cooling techniques are there, and nowadays people are using liquid cooling method. So we can have a heat sink like that. We will have a hole inside the heat sink, and we will connect that compressor. So it will pump the cooling cold water inside the heat sink, and while the coming out from the heat sink, it will pull the heat. So these kind of cooling techniques are there. And then thermal modeling. So and we have a softwares to analyze the thermal things, which are the devices will generate a heat, and which are the what are the techniques we have to use, and what is the fan speed should be there to reduce those heats and all. So we have to model the thermal things also. And then real world testing methods. How to test these things to analyze the losses and yeah, improve the to analyze the losses and how to improve the efficiency. We have a spice simulator, and the spice simulator is used for to simulate the switching devices and converters and everything. So we can decide. So once you design the gate drivers, devices, switching devices, and then your converters, so we can simulate in either spice simulations, or and we can use MATLAB also to test their performance. So we can analyze the performance of gate driver. What is the propagation delay? What is the rise time? What is the fall time of the gate pulses? When the MOSFET is turning on? When the MOSFET is turning off? So we have to analyze those things also to reduce the losses. So it will be helpful for improving the efficiency based on the performance. If you want to improve still more, so you can redesign your gate drivers and IGBT and MOSFETs. Again, so after the simulations, we can go for the lab measurement techniques. So usually before designing the product, we have to simulate and we have to test our converters in the as a prototype. It's called a proof of design. We'll call proof of design usually how it is working in the simulation, and we should achieve the same performance in that prototype also. So once it proved, we will move to that product manufacturing. This is called the lab measurement techniques. So we can analyze again with the hardware after the simulation, and then thermal imaging for the heat distributions. So if you go for the high power applications, we can't touch our product. So high power, high voltage, high current. They have used temperature sensors and to measure the heat sink temperature, to measure the MOSFET temperature and other inductors, capacitor temperatures. So it will create abnormal heat also, 70-degree, 100-degree, we can't touch that. So to avoid that, some thermal imagers are there. It will access it's a kind of camera only. So we can focus on the heat sink and MOSFETs or inductor, anything. So it will capture that only the heating part, where it is heating and what is the temperature there. So we have to analyze these things also, thermal imaging, to avoid that temperatures and heats. And then what is the future trends in power electronics applications? So we can assist artificial intelligence for the optimization, for the gate driver design, and for the converter design, for the switching control technique design. We can use AI things. So how the AI things works in power electronics applications? We can use machine learning for predictive switching control, to use to say that soft switching or hard switching. So decide that we can use machine learning how the our converter is going to work. And then AI based gate driver optimization is there, and to reduce the turn on loss, turn off loss, and then dead time considerations and EMI considerations, everything. So these things are for these things we can use AI for the gate driver design. And then losses and efficiency predictions. So we can use artificial intelligence for these things also. How the load is going to vary the next day, and so if you consider these power grids, so based on that power demands, and based on that how many house we are using inside the are there inside the city. So based on that, they are going to supply the power to the AC grid. So we can use AI in that now to predict that losses and efficiency, how much load is required, how much current is taking, and how much losses are there, how much efficiency is there, and we can predict using AI to reduce those losses and to improve the efficiency. And then we can use AI for temperature fluctuations also, when it is changing the temperature, and some aging effects are there. MOSFETs and gate drivers will work for some period. It will not work if we design now. It will not work for the 10 years, 15 years, 20 years, like that. So some aging effects are there. So we can predict those things also using AI. So these are all AI assisted optimization. So what is the next gen semiconductors? So earlier, as I told earlier, they used thyristors for the switching converters, like SCR, triad, diag. So like that switching devices, they were used in the 80s and 90s. So after that, they designed MOSFETs and IGBTs also for the switching devices. So so that they have improved the efficiency, and then they reduce the losses based on that. So now the next generation, if we look on that, and SiC device and the GaN devices are booming. So it is coming with very less internal resistances. So if you consider those things, internal resistance and all, internal resistance, internal capacitance, it will be helpful for this to reduce the switching losses and conduction losses, so that we can improve efficiency. And then if we compare these SiC MOSFET and GaN MOSFETs, um, with a normal MOSFET and IGBT, these SiC and GaN MOSFETs will work for very high speed. It will work for very high speed, and it is coming with a very internal low resistance. It will be helpful to reduce the losses and improve the efficiency. But the one thing we need to consider, the voltage and current ratings. Those SiC MOSFET and GaN MOSFETs are only available for the lower voltage and lower currents. So based on applications, we can choose those devices to improve the efficiency. So, and then smart switching devices. We can use smart switching devices like soft switching and hard switching, like that. So which will be the good to reduce the losses, and which will be good to improve the efficiency. And it is depends on that switching technique also. So if you consider this inverter, so we can use the sine PWM technique, normal 120-degree conduction mode, 180-degree conduction mode, and space vector PWM techniques are there. And for the single phase inverter, again totem pole converters are there. The totem if you compare these things for the single phase inverter, totem pole is giving very it's reducing losses, again the conduction based on the conduction period. So totem pole loss will be good, will be better than sine PWM and space vector modulation, or 120-degree conduction mode or 180-degree conduction mode. So it will reduce the losses, and it will improve your inverter efficiency. So based on that, we can find some other switching techniques to improve your efficiency by reducing the losses. So these things are there in switching behavior and improvement of efficiency. If you have any questions, you can ask me.
Participant, if there are any questions, you may post the same in the chat box so that our chief guest may answer you. If there are any questions, kindly post the same in the chat box. I think there is no questions. So we formally end this session. Thank you, Vasumani sir, for accepting our invite and being with us. Though in your busy schedule at L&T, you are provided time for us, sir. Thank you very much. Thank you very much for your love and accepting.
Thank you, Tony, for giving the opportunity.
Okay, sir. Sir, you can take a leave, sir. No problem, sir.
Sure. Yeah, thank you.
Participant, the chat box you might have seen with the feedback link. The feedback link has been